Okay, good morning. Welcome to our talk this morning, which is entitled Across the Board on Apple Arcade, Putting Dots Through Its Paces. And this talk is going to be delivered by Matt Rubin, myself, Neil Hutchinson, and Sam Royal. And a quick outline, do a quick introduction, dots primer, which won't go into too much detail, cover some of the crash camera systems in the game that we produced with dots, the dots rendering systems, and Sam's going to talk about automated performance monitoring, which gave us the confidence that we were delivering something worthwhile. So by way of introduction, this is Dr. Boom, the antagonist in our product, which was Detonation Racing. And this was developed and published by Electric Square, which Sam is representing, and with some help from Alphabet, which is Matt and I. And the platform was Apple Arcade, which implies a large range of device capability from Apple A8 powered devices such as iPad mini 4th gen and Apple TV HD, all the way up to 28-core Intel Xeon powered Mac Pros. So hopefully this video will work. It's just a taster of Detonation Racing. No sound, sadly. Okay, so this talk is a bit of a retrospective because this was released about a year ago now. So I'm just going to go through some very superficial information about dots in general. And so to summarize some characteristics of classic Unity, you kind of have multi-threaded core systems such as particles, physics, and rendering. But your game code was hard to parallelize because fixed update, late update, and coroutines were all executed on the main thread. Generally, there's quite poor support for SIMD, and the Unity engine.dll APIs were not thread safe. And one thing about Unity, classic Unity, was always lengthy loading times. So step forward new Unity with its data-oriented tech stack to try and address some of those problems. And our dots isn't really a single thing. It's kind of a grab bag of new systems that are delivered via the package manager, so it's not shackled to Unity's release schedule. And some of these aren't specific to dots. For example, native containers you can use in classic Unity projects, for example. So just to go into some very light detail on the ECS, this is kind of the beating heart of dots. And it's an abbreviation of entities, components, and systems. And so what's the motivation behind dots and data orientation in general? Well, this graph plots processor versus memory performance for the last 40 years or so. And it's known as the processor versus memory performance gap. And note that the y-axis is logarithmic. So there's a huge gulf in performance between processor and memory. And there's an interesting plateau that happens between 2005 and 2010, and that coincides with the general trend towards higher core counts and moving away from the search for ever higher clock speeds. And so what magic and Unity are using to try and address this problem? Well, it's kind of this. So here's a block of memory. It just so happens to be 64 bytes wide, which is the size of a typical cache line in a modern processor. And in an object-oriented setup, it's kind of exemplified by this. You might want to access a single byte in a structure that's in an array of structures. And your access pattern might look something like this. Now, what's going to happen at the hardware level, for each one of those bytes that you want to read, a whole cache line of 64 bytes is going to be moved from main memory into your cache, but you're only going to use one of those bytes. So all of that work is effectively discarded. And there may be cache prefetch hardware, which might load another 2 or 3 or more lines. But you're not really taking advantage of that because you might skip over and then read another byte from another cache line, and effectively you're missing cache quite frequently. So what DOTS is trying to encourage is access patterns a bit more like this, where you're reading, the cache line is moved in from memory to cache, and you access all of the data within that cache line, making the best use of what the hardware is doing behind the scenes. So just to throw some ECS terminology at you, entity worlds are the collection of the component data and the entities, and they are load in place, which makes it really quick to load. An archetype is a unique set of component types, and entities of the same archetype have their component data stored in what Unity refer to as chunks. And these chunks are 16K in size. Something to watch out for is changing an entity's archetype, which means adding or removing a component, is very slow, and they call that a structural change, so you have to manage these carefully. In our experience, which may have moved on now, but editor integration with ECS was quite poor. For example, you can click on an object in the scene view and see its state in the inspector. There was the entity debugger, but that's a new tool, and it takes some acclimatization to get the best from it. So if I can summarize ECS, I would say it has a very steep learning curve. And one of the other core parts of the ECS to try and take advantage of those multi-core processors is the job system. So I'm hoping you can see this is a scrolly video of some code. It's the car parts system in Detonation Racing on this play. Really just wanted to give you a flavor for some of the semantics and syntax inside a system and what the job system is doing here. So basically you have a schedule method, which is executed on the main thread, and it's the purpose of the schedule method for you to set up your jobs and add that to and submit them to the scheduler. And within the schedule method, you want to kind of handle your dependencies and how you're going to chain your jobs together. And at the end of the schedule method, it returns a dependency handle that then can feed into another system that you want to set up jobs for. You may notice, if you can read that, unfortunately, I think it's not come out too well. The jobs themselves, here we're using an iJob for each, which will set up a job for each of the entities of that archetype. But that means that you could get quite a lot of micro-sized jobs, which can kind of bog down the scheduler. So there are alternatives to that. An iJob chunk, for example, will iterate over the entire chunk. So we set up a job for an entire chunk, and it's your job to iterate over the entities within that. Pause this vid and move on. So just throw some job system terminology. Race condition detection is built into the job system, which is a nice feature. One of the challenges of writing multi-threaded code is you can often create these race conditions. If you are, using the memory access semantics, so you can specify members to your jobs as being read-only or read-write or write. Setting that up correctly ensures better parallelization, so the scheduler can parallelize your jobs better if you set that up correctly. It scales very nicely with higher core counts, but watch out for lower core counts because you can starve the job manager. So we had a situation in Detonation Racing where Fmod was basically camped out on one of the two cores, So the job scheduler didn't get a chance to run any of the low priority jobs. There was quite a few hoops to jump through to get any debug rendering. So if you were trying to do something to work out what's going on inside using debug rendering, it was quite a challenge, and no console logging or a search from burst compiled jobs. You could turn burst compile off and get those features if you wanted to, but the performance was a lot less. And so to summarize the job system, I would say it's fit for purpose. It does what you need it to do. It's got all the features there. Race condition detection is very nice. So yeah, it gets the job done. And dots physics, I thought easiest way to go through this would be to look at a profile capture. So this has been captured in Unity's profiler on an 8-core machine. And so at the top, you've got the main thread. And underneath that, you've got the traces for the worker threads. And notice, so with the physics system, it's unlike any physics system you will have used before, unlike PhysX or Havoc. It's kind of, you have to do it in stages. So the first thing you need to do if you're going to do any physics at all is build the physics world. And that has to be done each frame. And if you're in a fixed time step situation, you might have to do it multiple times a frame. So this is where we're setting up our, building our physics world. We insert here to the left of this trace, and now the car physics system, that's our handling model. And then subsequent to that, so there we apply our forces to the physics bodies in the handling model, and then we step the physics world after that. You might notice that the jobs for the systems don't line up. What really essential is that you set up your dependencies, your job dependencies, so that they run in order and it's not dependent on you waiting inside the schedule method, because that's just going to slow everything down as you wait. And then following the step of the physics world, you do an export. So that just writes the data back from the physics internal representations to the component datas. And after that, the chase cam system can then use that data to update its position and orientation. So you can see from this trace that it's quite sparse in terms of the processor utilization, but this is an 8-core machine. It looks quite a lot different to this on a 2-core machine. And as I said previously, we needed to do this twice because we ran our physics at 60 frames a second. So we just go back and rebuild the physics world and go through that process again. So just some notes for dots physics. It's stateless, which means that internally it doesn't maintain any state outside of build physics world and export physics world. So that means no overlapping pairs cache, no bounding volume hierarchy cache, or any of that stuff. Which is great for determinism. It has an elegant design, and it's really quick. And it turned out to be the perfect physics system for Detonation Racing. One thing to watch out for is there's no concept of sleeping because it's stateless. So all of your dynamic bodies are going to simulate every frame. So if you're building stacks of crates, this is not going to work out well for you. So you might want to implement some kind of sleeping within your own code. Some gotchas with dots physics. It can struggle with gnarly collision meshes, so you would do well to weld your verts and keep your meshes watertight. But you do get callbacks, so you can filter collisions to clean things up if things are starting to get a bit janky. And we could have gone a bit more like all in on the dots with our handling model. We had, I guess, a historical handling model, which was object-oriented, and ended up with it just being a kind of a monolith of object-oriented code within the dots framework. We could have pulled that apart and made it much more dots friendly, but in the end, we didn't have time for that. And we had to reverse engineer parts of the internals of the physics system to get it to fit as cleanly as we did in the end. But I would say that overall, I love the dots physics system. I think it gives us a glimpse of the future, what physics could be. I'd be delighted to use it again in a future project. So one question that you wanted to consider is dots suitable for my project? So I kind of summarize it in the flowchart. So do I know what my game is? If not, then definitely don't use dots. It's not a good choice for prototyping your game ideas. That is obviously the core strength of classic Unity. And if you do I have a realistic budget and schedule? If you don't, then don't use dots. You're going to burn a lot of time at the early part of that learning curve, that you may not recoup if your budget isn't adequate. And do I have CPU performance challenges? If you don't, so if your game is like it's a big meta loop, or perhaps it's a match 3 game or something, the UI elements are all going to be done in UGUI anyway, so you don't want to be using dots for that. And so if your answers are, if you get to this flowchart to the end, well, maybe use dots. You're going to have to consider it carefully, but it's a good option if you've got some like hard real-time challenges. And so my final slide, I would just say that with greatest respect to Unity for pushing in this direction. We've had object-oriented as the kind of primary paradigm since the mid-1980s. And maybe it's time for data orientation to take off now. I'm going to hand over to Matt, who's going to talk a bit more about some of the crash camera and rendering systems in Detonation Racing.
Hello, my name is Matt Rubin with Alphabet Limited Studio. I'm going to talk about crash camera system rather quickly, and then we'll drill down into the dots rendering system and talk about some of the performance problems that we encountered during the development of Detonation Racing. So first off, just quick sort of slide on how we implemented a bullet time system during our crash sequences to allow kind of a cinematic slow motion effect. That we kind of had a target timescale using kind of an ease in, ease out sort of interpolation within the step physics world code, which is part of dots physics, to kind of pick up on Neil's point on the handling system. We basically just scaled the delta time through the physics step, and that kind of gave us a slow motion effect. You could do this in classic Unity, as well as one other point is that the timescale also needs to be adjusted in order to get the set piece animation and the visual effects to play back at the same speed. So I'm just going to show just a couple vid caps of that. Oh, there we go. So yeah, ease in, ease out, back into real time, and then back into the respot. Let's play it one more time quickly. Bit of a vignette effect, and just trying to like engage the player a little bit more in these sort of moments of gameplay, which are kind of critical. And then we also implemented the same system using a sort of a look at target for when the player actually took out an opponent, and that kind of increased the player engagement through the gameplay sequence. They actually gave them some feedback that they did something that was actually sort of made them feel better, that they actually had some agency in the game mechanic. So just wanted to kind of give you a taste of some of the gameplay aspects that we implemented, but I'm going to go a bit more into a performance aspects of how we kind of approached our authoring of our levels. So Dots gives you a lot of scalable performance. We got a lot of work to do for update and rendering, as well as actual GPU work to actually push the verts and shade the pixels through the transformation lighting pipeline. So there's quite a wide range of performance capabilities between multi-core desktop sort of CPUs on the high end, as well as smaller dual-core mobile CPUs. I've got just a quick sort of bar chart from the Geekbench benchmarks that kind of show on the left the CPU scores, and then on the right the metal scores. You can see our min spec is that little green dot at the bottom, which is the iPad Mini 4th Gen. Not a very performant device. So trying to approach this problem to kind of scale our graphical fidelity across these different the device spectrum is quite challenging. It's basically a big balancing act. So we approach this problem as probably most people in this room do. Basically use quality levels to adjust your rendering features. So basically dial down the visuals on our low end sort of platforms. At the minimal, we needed to have a single shadow pass, but we weren't going to try to make it too much. We're trying to manage our risk here. And then we would increase our graphical fidelity on the high end, adding additional lights, post-process, HDR, standard stuff. One thing that's interesting in the URP shader settings, I just wanted to call out on the advanced section, is this tick box called SRP Batcher, which is just kind of a bit mysterious. So I'll get back to that later. We'll drill down a bit more into that. So our first sort of performance tuning approach, we kind of did some captures on the iPad Mini 4th Gen. The CPU profiler was actually pretty tight, but it was still it was within reason. It wasn't our critical path at that point. However, we did notice, as Neil pointed out, we were quite job heavy on our dual core mobile CPUs, and we had a lot of thread contention, and that caused us some issues that needed resolving. However, one thing we did find out was once we removed graphics jobs and disabled that feature on the low end, we were actually able to stabilize the rendering trace, and we got much more sort of like better performance out of that. That's something I'll also touch on later. And then the final point here is that we're vertex bound. When we actually did our GPU captures, we had too much geometry we were processing. These low end devices can really only handle around 500,000 verts per frame. I know that sounds ridiculous, but even iPhone 6s were handling several million. But once you get down to the Mini 4th Gen, it's pretty bad performing device. And this is the link to a Unity tutorial on performance problems on graphics that might be worth a look. So the SRP batcher, let's just drill down a little bit into this. So it's a tick box in your OP settings. If you actually look at the documentation of the batch renderer group, it's actually defined as documented as an experimental API, and it's only in use by the DOTS hybrid renderer. Sounds interesting. I'm intrigued. As we kind of read a bit more, we can kind of see the add batch actually looks like it takes an instance count. So it's clearly utilizing instancing support, which is good, something we can try to take advantage of. And finally, the description of the add batch method, you can see it basically says, this command is persistent, and doesn't need to be called every frame. Now that's quite novel from a rendering engine. So this is kind of like a next gen sort of approach to a rendering system that's much in comparison to classic Unity's rendering engine. One other point to take home here is actually in the Unity engine namespace. This is all part of standard Unity. You don't need dots to use this. This SRP Batcher blog article is actually quite a good read. I recommend it. Gives you a bit more background. So one of the things we did is the SRP Batcher gives you a testbed that's up on GitHub. The link's at the bottom. We started like trying to build up this testbed to increase our experience with this new rendering tech. We did a rapid iteration technique by building up, bottom up, sort of increasing with a good of primitives and increasing our sort of vertex count as we went. And we kept adding primitives until we actually hit a bottleneck. And then we would back off from that threshold. Because we didn't actually want to tax the CPU and the GPU on mobile, because that basically is a power drain, and then we get into thermal throttling, which is another performance penalty, which we're trying to avoid. So profile on the way, understand your costs. Testbed captures really fast. Profiling in isolation can give you empirical observations that you can't actually find when you're profiling in your game itself. It gives you a lot more insight. I highly recommend it. Also, add on-screen diagnostics, debug diagnostics. It gives you, again, more information. You can kind of validate some of the work you're doing along the way. So we then added support for the DOTS hybrid renderer into the testbed, and that actually gave us a bit more insight as to what was happening within that code path. You actually get different rendering traces when you actually do classical Unity rendering, SRP batcher rendering, and the hybrid renderer rendering. They all have different CPU traces. So basically, these had subscenes, which is a DOTS concept, which basically holds your game objects and converts them into effectively ECS render mesh components at runtime. So the DOTS hybrid renderer is actually a concrete implementation of the batch renderer groups. You can actually see the code. It's worth having a look. It basically will pass an unperformed culling callback to the constructor, and that culling callback will actually perform view frustum culling and LOD selection on the CPU. But then it sets the results actually into this batch culling context visible indices sort of struct that gets passed to that function. So that's actually rather cool. So you can basically see it's a persistent command buffer. You're basically specifying which things are actually visible. That's what the GPU is going to chew on and process, and that's where your costs are coming in. So we thought maybe we could extend this culling system to actually, with a hidden surface removal technique, to reduce our vertex processing. So we implemented an offline visibility capture system. The main idea here is we generated an offline a priori visibility map by following the track spline. So we could specifically add a unique ID to each mesh renderer in our scene, and then convert that into a visibility ID in the ECS world. And then we would discretize the track spline into a fixed number of sections. And then we perform the track walk by just following the track spline, stepping along it, and then sample the number of visible pixels for each draw call or each instance. And then we could record those results of the render mesh instances into a per section visibility bit mask. Then the memory requirements here are pretty negligible. It's about, for 8,000 renderables, say it's about 1K. So if you had 50 sections, about 50K. Obviously, we had multiple splines, so it added up a bit more than that, but just something to keep in mind. And then you can actually logically order these bitmasks together for all the camera samples within a given section. So you're basically just running a lot of camera samples and you're saving that data so you know what actually is going to be visible. Make it clear, the bit is set to 1 if it's visible and it's 0 if it's not. So this is just a sample scene of one of our visibility scenes. Now, the main point here is it actually pulls in the same source geometry as our runtime in-game scenes. So this is actually a different scene that's never loaded in-game, but it's just purely purely constructed in order to run these visibility labs offline. So it's just a quick sort of slide on how did we approach this. We've in previous games where we've used this technique, we've used occlusion queries with DirectX, but there's no obvious way to get this working within the Unity framework. So on my colleague Neil's suggestion, we decided to roll our own based on a picking hack from the OpenGL days. And effectively what that system did, it just encodes the ID of each sort of draw call into an unlit color value into the fragment shader. Then you can actually read the pixels at the end of the frame and build a histogram of the visible pixels for each ID. So it's effectively like a low budget, low tech occlusion query, gives you the same information. It's also hardware accelerated though, because we're actually still using vertex and fragment shaders. One point though is that, as you saw in this previous slide, we have actual materials on our geometry. So we actually have to swap the geometry in with a unlit shader to actually approach encoding the ID into the color field. You can just see here, there's basically a red occluder that's hiding the green and yellow primitives behind it. Effectively, those would not be visible from this particular camera angle. So here's just a glimpse of the offline visibility capture running. You can kind of see everything looks in blue because we basically encoded from BGR going backwards. So everything looked pretty much blue. We never saw anything other than blue. It kind of gave you a report as it was going along the way, and we're doing multiple track walks, running out of time. So basically, we captured multiple runs in the play mode and captured runs, visibility captures in play mode in the editor using a custom editor window, which would perform multiple laps in different lanes, so like in the left, center, and right to kind of increase our accuracy. And then we'd also perform multiple laps in each track in different facing angles, like forward and backwards, left and right. And those would be recorded to different bit mask. And then we'd write those results to a visibility database object that would then be available at runtime for access. And then we also supported batch capture mode, so we could just run this through all our tracks and just leave it running. It took about an hour or so. This is just a screen grab of the visibility database, just kind of showing the scriptable object and all the data that we showed, showing all the different visibility bit masks that have been encoded in a U64 format. So some of the issues that you have to be aware of with this technique is make sure your capture resolution and aspect ratios are appropriate. Texture 2D properties, make sure you don't end up converting your color IDs or your back into a different form. So you need to make sure you use point sampling, and linear space color conversions can be a gotcha. Previous captions go out of date when the content creators are modifying the source geometry. So make sure you have some way of detecting that and disabling the calling at runtime if that's the case. Just put up a big message like CRC mismatch or something. Only apply these this sort of calling technique during the main pass. You don't want to do this during the shadow pass, and that's so you basically just need to make sure you've got the hooks in there to only do it during the main pass. And then also we found our histogram calculations was one of the bottlenecks during the capture, and so we wrote a compute shader for that, and actually increased performance about 30 times during the capture runs, which was pretty impressive. So at runtime, we want to discard draw calls that don't contribute to the final frame buffer. So we extended the hybrid renderer calling system to add additional visibility calling data. And that was basically plumbed into the hybrid chunk culling data ECS component. And then we would perform a constant time lookup of the visibility maps at runtime based on the player camera position and facing angle. So if it was like looking forward and left, we'd combine those two bit masks and then send that down into the hybrid chunk culling info. And we'd write this up to this visibility info into that component every frame before the hybrid renderer system ran. And note, this technique does not require structural changes to the ECS sort of scene graph. And additionally, the hybrid renderer will actually skip the vfrustum calling work for non-visible instances. So it's also a CPU win. And also one point to make is that we need to disable this sort of culling system when the camera strays too far from the track surface, which is where we've done all of our sampling. So in some of the crash sequences and whatnot, when we get different angles, we actually dynamically disable it. So we've done some trampoline tweaking. The main point I brought up before about how disabling graphics jobs, it's actually a project-wide setting. There's not an obvious way to do that at runtime. So we basically jumped into the trampoline and injected a Dash Force GFX MT flag into the command line parameters into the Unity player based on the device basically model version that you can inspect and just using Objective-C calls. And then finally, we implemented some lightweight perf timers in the native layer to basically capture our player loop CPU time, render time, time to present, and GPU time. I'd like to go into more detail on this, but please find me later because I'm running out of time. But I just wanted to introduce you to capturing this data in the native layer. So then you can do a lot of your captures in release mode and record that data to a TSV file that you can then export back to you can export the data back to C# land and then write a TSV file. And then that can then be fed into, that could then be fed into a automated perf test framework that my colleague, that Sam from Electric Square will talk about in one moment. The last point I just wanted to make is you can also validate these perf timers. This is quite a good technique. You can basically use the QuickTime player to mirror your screen on your Mac, and then actually capture video alongside with the performance gauges in Xcode, and it can really give you some good insight as to where your performance problems are coming from. That's all I had to speak to you today about. Now Sam's going to speak to you about the automated performance monitoring system that he implemented. Thank you.
My name's Sam. I did build and test on Detonation Racing, rolled that forward as well into a project we did called Warp Kart Racers that came out more recently. And particularly, I did automated performance monitoring for both of those. So question one, well, why do you want to automate it in the first place? And realistically, it all comes down to time. We had about 10 maps in both of those projects, give or take. You've got 26 devices that the iOS 13 beta that's about Detonation Racing time targeted. That's not even including macOS devices, tvOS devices as well. A couple of game modes, multiply all of that out, you're talking 500 test cases that you need to look at. And there's all sorts of other axes you can turn on as well. So difficulty levels, OS versions on the devices, charging, not charging. A couple of minutes a map, that adds up real quick. Multiplayer is also a huge problem as well. So Warp Kart Racers, we had 8-player multiplayer. We managed to gather 8 people together like once a week for like half an hour, maybe an hour to look at the game. And realistically, we had more important stuff to talk about than whether we were in frame. On top of just how long it takes to get the numbers that you need, cycle time is also really important if you're doing this kind of thing. So faster feedback to the team is always better. Problems are cheaper to fix earlier. You won't have context switched away. Maybe you can try stuff and figure out that it's going to work before you do it to every level in your game. So we had some targets we were trying to hit 5 minutes after your submission. We've opened the project. Cool. Now we're catching compile errors, the kind of it works on my machine kind of stuff. Within 30 minutes, we're checking your content. Some of that is not necessarily performance related, but stuff like texture sizes, texture formats, that's all really good stuff that could have a performance impact. So let's detect that early. Within 45 minutes, we're playing the game in the editor and getting some numbers out. Now, it's true, we don't ship the editor to the person who plays it eventually, but your dev team is going to use it all the time. So it's really important to keep on top of that as well. And then within 90 minutes, hopefully we've built the game, we've got it on a device, and we're getting you some good actual proper numbers back. Why might you want to do this? Well, for confidence, really. The team can be confident that they're doing good work that's performant. Leadership can be confident that you're hitting the targets that you need, perhaps even contractually obligated. And it's also making sure that you don't have this big looming performance task in the distance of someday we're going to have to fix all this. It's important for your clients and partners to get that confidence as well. So if you always ship them a performant build and show them performant builds, you can use the time you have with them to talk about more important stuff than are we just going to get in frame on some low performing device. It gives you confidence in your strategies as well. So I said earlier about trying stuff and getting feedback. That's really important. Also, when you do come up with a fix for something, you need to know that it's properly worked across the board, and this helps with that massively. And I'll talk about it in a second, but it really gives you confidence in taking risks as well. So when? Well, during development, really important, obviously, the whole way through, but particularly around release, that's when you're going to have to kind of pay the piper, as it were, and come up with the real actual figures and be sure. And then later, post-release as well, updates. One thing about updates is that the team might be a bit smaller as well. So if you didn't have capacity to do performance monitoring before, you certainly won't once most of the team has switched away. What does that confidence look like? Something like this. This is a high-level dashboard for Detonation Racing showing quite a lot of green, which is great. Everyone can sleep soundly at night. There's a little bit of a problem on like one device, but that's where the team is focused, and you know that everything else is fine while you drill down on that and fix that up. There's other side effects you get from this as well. So if you're not getting any data through at all, maybe from a map, maybe from a game mode, maybe from the whole game, that's telling you there's a problem, not necessarily performance related, but it's really handy to know it. All of these metrics you're collecting as well, any statistical outlier is pointing to some kind of unusual behavior. It's certainly very cheap to collect these metrics most of the time, so you might as well collect them now, analyze them later. It's really useful to be able to come up with smart questions later in your project and go back and ask those questions about how things were in the past without having to dig up old builds. I mentioned risk earlier. Well, change can be risky, and risk is generally quite expensive. So this kind of system can really help make that much cheaper for you. If you're worried about something having a performance impact, you can find out. And it's very useful to be able to encourage taking risks. You can throw a whole bunch of stuff at the wall. Some of it will stick, will work, and will be good. And maybe some of it won't. But as long as it's not costing you too much, then that's absolutely fine. If you're going to do this, it's really important to remember it needs to be pretty much entirely hands-free. So even a single manual step, if someone needs to like accept a dialogue on a device or copy a build around or something, that's going to be a big, big problem for you. And more on top of that as well is that your automation system doesn't keep office hours. It's there 24 hours a day. It can be doing things 24 hours a day. And you might have a distributed team as well. So maybe they're in different time zones. So they don't really want to assign a person to, hit buttons on a device that might also be in a different country. Just as an example, I've got the build and test schedule from ES there on the screen. You can't really see it, but 12 a.m. to 5 a.m. is very, very busy, but pretty much the entire UK dev team is in bed at that point. It's really important to remember that you need to separate this from the game itself. You are not going to ship this at the end of the day. You've probably got a whole bunch of flavors that you can cut of your game. So you might have debug with, no performance implications whatsoever, no expectations, all the way through to like development where you work on a day-to-day and then the release. And you really need to know your kind of deltas in terms of performance between those. So as a real world example, on our projects, we found from release to performance, which is just enough to get the data out of the game, 2% impact. To go from performance to test, which is where you've got debugging information, but nothing you can actually like sit down and use on the device, 10%. And then getting that on-device stuff that really helps you dig into these issues, it's going to cost you another 5%. Earlier is definitely better with this. So the earlier you can integrate it, the quicker you can work with confidence. It's generally true as well that in these kind of projects, resources are more available earlier. So best to get it out of the way and kind of save the good stuff for later. And you can set your expectations early and then stick to them, which is what I was talking about earlier in terms of confidence, right? How to do it in terms of hardware? Well, you'll have a coordinator. We use TeamCity, Jenkins is out there, Circle CI, plenty of products to do it. That will manage a pool of agents for building and testing a game, more than likely. A lot of ours are shared, so they'll cut builds most of the day, and then they'll turn around and be one of our reference devices later on. You'll have a whole ton of devices, more than likely, some mobile, some desktop, some plugged in, some networked. But whatever happens, I can guarantee there will be lots of wires, and it's really important to buy good USB hubs. We have a cooldown period in between our test cycles. That is like a thermal cooldown period to actually let the devices just chill out a bit. But it's also an opportunity for us just to get some more juice in the batteries. This is a little GIF just showing a 10-device suite booting up Warp Kart races, trying to enter a multiplayer game together. I think this is really kind of just cool to look at. We also had a couple of big TVs in the office as well. So that's pretty nice for people just to be able to kind of wander past and see your game play in itself. And once or twice, I've even caught an issue or two just by walking past and thinking, man, that doesn't look right, If you're going to do it, try and use existing tools. So Unity's got the test runner built in. Unreal's got the automation system. They're both really good for this kind of thing. Arranging situations in the game, waiting for stuff to happen, feeding back results. And I should give a massive shout out to iOS Deploy. You can find it on GitHub. That's effectively essential if you're going to do any of this kind of thing with iOS devices. So you've got your data, great. It's very cool, but the team wants conclusions. So you need to transform it into something that's easy to check, easy to interpret, and they'll be more than happy to dig deeper when necessary. So we're going from like the raw numbers in a file, maybe to a database, and then to some kind of visual presentation. For Detonation Racing, we found that context was the most important thing. So we've got track splines with hotspots. If anyone asks you, why a performance issue is there, well, the first thing you want to know is where and when it happened. So all of our big events in the game are on top of all our graphs showing us when stuff happens so we can kind of correlate it. What that will achieve for you is hopefully to go from something like on the left where everything's a little bit dicey to something on the right where everyone's nice and happy with the performance. Once you're done with one project on this as well, you can take your tools with you, hopefully. So your team should be familiar with the concepts and implementations. You'll find it much easier to pitch this if you've got the proven code to bring across and some results to demonstrate. And you can be ready to go even before the game itself. So that's going to be pretty much as early as you can go on the do this early kind of axis. And just finally, some real world examples. Well, here's the audio subsystem in Warp Kart Races. Starts off a bit squirrely. We try something I've marked as test. Great. It does wonders for our frame time. Didn't quite work in some other aspects, so we pull it out. Later, we submit it properly, and then we hold that good performance all the way through. There are like 6 times we deviated, but we quickly brought it back in line. And a pretty typical graph, draw calls here, starts off kind of dicey as people are trying stuff and iterating on the level. Art comes in, makes it very heavy. Then we do an optimization pass, and it's nice and flat from there on. Same for a CPU in blue, never really changed that much, but GPU, again, optimization pass hits. Down it goes, stays nice and low. Hitches as well, so you can see on the low end, it was pretty bad, and then it got better. On the high end, it wasn't so bad, but it got really good. And we could kind of validate all of that. And you've got some other stuff you can do too. So maybe you've got some customization, maybe you've got some user selectable settings, maybe there's really specific device configurations as well. So like Apple TV 4K can push out 4K HDR, that's got performance implications, so get one of those set up on a desk. Shader warm-up's another thing that's really important in terms of performance. Well, capture back that data too. So what shaders are warming up and when. You're obviously going to be loading into a lot of situations, so grab those load times as well. And don't forget that you can test the front end with this just as easily as the actual game itself, especially if you've got some like 3D scenes or anything that's pretty animated, you know. And what I will say is if you do build this kind of system, you will definitely find that there are always new platforms, new devices, new metrics to capture, and people will always want new reports.
Right. Well, just to be clear, we were just a small sort of part of a much bigger team that we just wanted to acknowledge the work that was done in Electric Square by Tim and the Electric Square crew. As well, we also collaborated with Paper 7 team, Alice, Ryan, and Dave. And then also we want to give a shout out to the Unity people, particularly Jussie and Sebastian and the hybrid rendering team who gave us a lot of help when we asked questions, as well as Liz and Victor in developer relations who also gave us a lot of information and were really instrumental in us releasing this game on time and with high quality and high performance. Thank you all for listening. We realize it's a bit of a quick sort of format for 3 different speakers, but here are emails. We'll also be around after the session if anybody's interested in asking further questions, but please just reach out. We're always happy to talk to other game devs in the community. Thanks again. I guess we do have some time for questions if there are any. Yeah, I think I'm supposed to wait until you get the microphone, so one second.
Thank you. Hi, my name is Bartosz from Ubisoft. So I noticed that you used ECS pattern in Physics Engine and also in Graphics Engine. And I would like, I would like to ask you whether you could share some thoughts on the main bottlenecks of using the ECS pattern you experienced, and also some scenarios when the ECS pattern is suitable to do things and when you should never, ever use it.
Yeah, it's a really good question. I think a lot of, you can easily go all in. I think really if you're trying to do something where too many game objects in a more kind of classic Unity sort of framework is showing performance problems, I think, and those that sort of system in particular, the vehicle handling, it's highly parallelizable. It's a good fit for that. Being too heavy on job, basically burdening the job system will create problems on lower core devices. So on desktop, it's fine. But what we found on mobile is that we did have starved threads, which including just part of the DOTS memory management, sort of automated memory management system for releasing temporary memory allocations, for instance, would also get starved, which then created problems subsequently down the road. So I think to try to answer your question specifically, find a problem that's highly parallelizable, that is a performance problem in a more single-threaded traditional architecture, and then try to parallelize that with DOTS, I think may be a good first step before just saying, oh, we really want to like just dive straight into the deep end of this new tech stack. It's really cool and it gives you a lot of capabilities, but it, great responsibility, with great power. great responsibility. Excuse me. There's 1 minute left. If there's anybody has any other questions.
Thank you.
There's one more question here.
Hi, just regarding your pre-computed visibility mesh, you said you use it just for the main pass and not the shadow pass,
Yes.
which makes perfect sense. Was there any additional pre-computed passes for the shadow passes for static geometry, or did you not see any gains?
Yeah, no, it's a really interesting question, and I think I've worked on this. I've done this this is the third time we've implemented this system, and I've been quite curious how the best way to approach it for shadow map passes. Clearly, it's possible to extend the system, but really one of the drawbacks of the system is if you have large buildings, say with large shadows that are cast across the track, and that building is not visible in the current frame, it actually will be culled, so you won't actually see the shadow. However, we try to take a more conservative approach, where we try to include is like fairly large field of views in our captures, so that we try to avoid that problem just empirically by observing where we saw these issues occur and just ensuring that we ended up capturing those. I think time's up, I'm afraid, but I think it's a very interesting problem, and I think it would probably be version 2 of the visibility system on the next go, maybe 4th time lucky. Thank you.